In all things, I will give you praise. Hey, in all things, I will shout for joy. In all things, my heart will rejoice in you, Jesus. For you are working, always working in my favor. In all things, I will give you praise. In all things, I will shout for joy. In all things, I will rejoice.
Let's conference today to the glory of your name. In Jesus' mighty name we have prayed.
Let me also recognize the presence seated here with us, the distinguished professor of chemical engineering, Engineer Professor M.S. Wabili. I also recognize all the professors, readers, and distinguished participants that are here for today's session. May I bring to the high table the big masquerade for today, Engineer Dr. Emi Goko. Please help the presentation. Immediately, if you are ready, I would like you to flash the presentation of the keynote speaker of the day. As I ask him to stand for me to read a brief citation. But before I do that, let's have some remarks from the dean.
Thank you, Professor M.S. Wabili. And the distinguished award of sympathy for the keynote speaker, Engineer Dr. Emi Goko. Distinguished colleagues, I want to welcome you again on the second day. By the grace of God, we are the part of history. We are beginning something that will feature the number of attendants will be unimaginable. I could remember when we were here. In my class, I'm not sure we all to pay. The whole entire Futo, I'm not sure we all to 500 or so. Before we do it, and that Futo is almost 25 to 30,000 people. We will all say what they do. They cleaned our everything was free and was good for us. But now the reverse things have changed. So you will take this word that the first time that's conference that tell us was very too much. But in time it will be versus crowd. Is our prayer. And today, by the grace of God, as the people read, we have a distinct alumni with high global visibility. What else? He made a lot of sacrifice to leave his base in the living Lord, to attend this call by his alma mater. For this intelligent one can do it. I want to play plays. I don't want to see this empty seat in front. Don't allow seat before you. Call it forward. Let us so that it will give the cameraman good scene of the event. I don't know that I want to give you man. That's the beauty. That shows that the people are standing here. I think it's better. Thank you for the performance coming. I appreciate it. So let's go on the process. That's the point
for today's intellectual harvest. Like I mentioned yesterday, today is jam-packed with a lot of programs. And I'm happy we are all here to be very much involved in what we have today. Ladies and gentlemen, may I humbly ask the distinguished plenary speaker for today to please stand as I read a brief profile of you. Dr. Eni Oko is an associate professor in chemical engineering at Newcastle University, UK. Dr. Oko has over 15 years combined industrial and academic experience and has successfully developed and led research and innovation projects on different energy transition technologies with a combined portfolio of over £3.5 million, including ongoing €1.5 million EU MSCA catalyst project or renewable fuel production in collaboration with 14 partners in China, South Africa, Nigeria, Finland, Norway, and the UK. Dr. Ko has recognized expertise in energy transition. Dr. Ko's co-authored paper on carbon oxide capture and transport, published in Process Mechanical Engineering, was Sage Publishing Best Paper in the year 2014 and was awarded the Goodwood Prize in that same year. This paper was also the basis for the UK Department for Business, Energy and Industrial Strategy 2020 report titled Carbon Capture, Usage and Storage Development at Dispersed Sites. Dr. Ko's review paper on CO2 capture technologies was International Journal of Coal Science and Technology Impact Factor 6.9 best paper between the year 2017 to 2019. Dr. Ko was awarded Future Leader in Carbon Capture Award in the year 2024 by the International Congress on Separation and Purification Technology and International Carbon Capture Association. Dr. Ko was also joint winner of the Nigerian Prize for Science, the largest science prize in the continent of Africa, for his collaborative work in process intensified carbon capture and utilization. The research of Dr. Ko in energy transition has been published in over 40 leading journals and presented at over 20 international conferences. Dr. Ko has supervised and co-supervised 10 PhD students, 4 completed, 38 master's degree projects, 1 co-supervised PhD at the University of Pretoria, South Africa, 1 co-supervised PhD student at African University of Science and Technology, Nigeria, 3 visiting PhD students from Southeast University, China, 1 visiting PhD student from Hunan University, China, and 1 visiting PhD student from the Federal University of Technology, Nigeria. Ladies and gentlemen, I present to you the plenary speaker, the keynote speaker number 2 for this conference, who shall be talking to us on renewable energy and clean technology, the role of engineers in shaping the energy future, and his title is actually on the role of engineers in an era of energy transition. Let's make welcome engineer Dr. RENEWABLE.
So I'm now in this area, and the university is lucky to be able to work universities, one of the Russell Group universities. So in the UK have around 147 universities, quite a lot for a small country. But yeah, and out of that, 24 of the universities are considered Russell Groups, and that includes Cambridge, Oxford, and the rest of them. And Newcastle is very privileged to be among the Russell Group universities, which are 24 most research-intensive universities in the United Kingdom. We are around 129 based on the latest US World Ranking. We are at the middle of the town. With this, the first picture here was clear enough. You can see our School of Engineering is just by the west side of the campus. You can see Newcastle United Football Club and just down the street from where our offices are. And the second picture here is showing you our technical engineering building, where I'm based, and then other places are our student union building and the rest of them. Our department, our chemical engineering program, we are very privileged to have the only student-run brewery across Europe. So we have a brewery that actually produces beer that is, that is sold around the region. Okay, so and the brewery is entirely run by students. It's entirely run by students. So at the end of every semester, the students have lectures, they recruit new people that will be marketing manager, that will be production manager, and the rest of it. And it is actually running on the side of the institution. It's very profitable. It's making money, that we are able to sustain the project. So in our program, in our discipline, we don't use the department formats that we are very familiar with here. So at Newcastle University, what we have in the School of Engineering, our School of Engineering is equivalent to what we would call a department here in the Florida. And with this School of Engineering, we now have disciplines. Okay? It's quite ironic, but yeah. So our disciplines are our chemical engineering discipline, and in our discipline we then have research groups. So at the discipline level, we have people that run these programs for teaching purposes, and for research purposes, we are classified on the basis of research groups. And I am part of the process intensification research group. And within this group, we have different colleagues that work on different areas, and we are particularly big on reactor development. And the process systems engineer, so most of my work is computational modeling kind of work. And what this is the kind of system I use here. Sorry, we are moving a little too fast. And what we have the high performance computing cluster, which is where I work most of the time. In terms of my research, my work is mostly around different areas of energy transition, process systems, synthesis, optimization, modeling, and stuff, focusing on CO2 capture and utilization, hydrogen production and transport, energy systems analysis and integration, and energy storage. In the past couple of years, matter of fact, we've been very privileged to work with a number of research projects on different areas of energy transition, and the total of that over 3.5 million research portfolio during this year. So today I want to talk about energy transition. I know that you probably have heard a lot about energy transition, but please allow me to just go from the basics, especially for our students that may be unfamiliar with this word. So to talk about energy transition, we want to talk about where we are at the moment and where we are going in the future. So at the moment, where we are with respect to energy, we focus on procedure-based energy system. Okay? And this is energy transition have to be contextualized in some way. So in Nigeria, the government energy transition plan, the Nigerian government energy transition plan, launched under the one, included gas as part of Nigeria's strategy for delivering energy transition. That is because gas has significantly lower carbon content than the other fuel types. So energy transition means shifting from the type of energy that we use now to a different type of energy in the future. We'll talk more about that in a bit. Why has this become a subject for anybody to bother about? The first one is climate change. The figure I have here, this is something you are not seeing. I'm going to give the slide with Moses and Dr. Cora. So if you are interested, you can have a look. Alright, so the first one is climate change. And of course, climate change is highly debated, but what is not debated is that the Earth's surface temperature is rising and been on the rise in the past 50 years, since 1950, 1960. It has risen dramatically during this period. There is no disagreement on that. Everybody agrees on this. Where there are disagreements is the causes of this rise. Now, the climate change people believe that this rise in temperature is related to rise in greenhouse gases, and of course, as engineers, we are not politicians. It's not in our place to start debating on what this side of the room believes and what the other side of the room does not believe. Our own role is to develop the technologies that can be used to deliver solutions. Okay? So, because there is rising global warming, different parts of the world now believe that the main source of CO2 into the atmosphere. Hello? The main source of CO2 into the atmosphere is the use of fossil fuel. Okay? It's the use of fossil fuel for different purposes. And one way that we can address this problem is to cut them. And that's why we hear about the word net zero everywhere. So in Nigeria, the objective is that we should reach net zero by 2060. In the UK, the objective is that we should reach net zero by 2050. Why these dates are important is because the scenario forecasts that have already been completed by different organizations show that if drastic actions are not taken, that by 2100 we will be facing more severe conditions. And there is a unwritten deadline of around 2070-2075 where we have to definitely get it right in the next year. Okay? So and this is what the second chart is showing here. So many countries including Nigeria target to reach climate neutrality what is called net zero between 2050 and designing or re-engineering the entire industry. So it's quite challenging to decarbonize it, and that's why there are key focus for transition. Because of geopolitics, energy security, we are familiar with what has been going on in Russia since the breakout of the Ukrainian war. Because Russia supplies most of the energy used across the world, Russia was able to successfully, in principle, drive many European countries into recession. Okay? Russia was able to drive many European countries into recession. They only did that because they control the energy assets for this country. That includes Germany, that includes the UK, that includes France, etc. Okay? France only was able to stay away from that because most of the energy that comes to this comes from nuclear. Right, so many countries now consider energy transition something that needs to happen for their own survival, because energy transition gives countries the opportunity to produce their energy themselves without depending on anybody. Okay? So it is a matter of survival for many countries, and not just a matter of from a green engineering background here. So the data out there says that there are limited amounts of course, finite amounts of oil, gas, and coal out there. Okay? And the proven recoverable reserves worldwide have under 100 years until they are exhausted. That is what the data says. Okay? That is what the data says. It doesn't mean that more sources will not be discovered before this time. But this is where energy transition comes in. Energy transition is about countries thinking about the worst case scenario, where these oil and gas and coal reserves actually run out completely. What will the countries do? Do we need to fold our hands and wait till these things happen before we start taking action? And this is what energy transition is about. So energy transition, if you don't take away anything, is motivated by 3 factors: climate change, geopolitics, and sustainability. So going forward, we have the pillars of energy transition, the pillars that drive energy transition, that forms the right support for energy transition. Okay? The first one is decarbonizing. We want to replace fossil fuel with renewable or low carbon energy. So under that context, we are talking about renewable energy technologies, and you know them. We are talking about carbon capture and storage technologies that are integrated to energy generation, and we are talking about fuel alternatives, low carbon fuel alternatives. A very popular example of such fuel is hydrogen, and then you also have the DME, dimethyl ether fuel, which has been proven to have similar characteristics to oxygen. We can, in principle, use them in diesel engines, okay, without needing to rebuild the engine. The other one is to re-engineer existing technologies. How can we re-engineer existing technologies? Talk more about that. Or how can we build entirely new technologies, okay, that have better efficiency than what we have today? So, come back to energy generation, where we have the steam cycle, one-time cycle, or we have the breaking cycle, gas turbine power generation. How can we design or re-engineer these technologies to deliver data efficiencies than the current do in Nigeria? Worldwide, anywhere today. Okay? Why is that important? This is important because, number one, 1% efficiency gain can avoid as much as 30 emissions per power plant annually. So this is based on global generation and very similar to gas power generation. So that means for gas power generation with efficiencies of say 52%, for instance, if we are able to redesign the system such that instead of having an efficiency of 52%, we can shift up the efficiency by even 1%, we will already be saving a lot of carbon emissions worldwide. So you can imagine if we make this cost across the world, we will be saving millions of tons of CO2 annually. A good example is the new generation of steam power plants that are called the ultra difficult to decarbonize. I've said that before. So why do we need to electrify? We need to electrify because in the industry, for us in chemical engineering, you have reactors. Okay, you have monster reactors in the industry that require thermal energy to function. Alright? Electrifying them means finding different ways for implementing this system without using thermal energy. In our homes, you can put solar panel on the roof of your house and you have electricity. It is not that way with hello. It is not that way with chemical processes. Okay? It's not that way with chemical processes. So we need to engineer those systems to lead to electricity heated reactions. Okay? So examples going forward, we talk about electrical heating for industrial reactors. This would be direct electrical heating. It could also be direct heating, which is what we call microwave heating. Then you also have what we call plasma catalysis. Okay, plasma catalysis. Plasma catalytic reaction is different from everything that we were taught in thermodynamics, for instance, in chemical engineering. Okay, plasma catalysis follows entirely different principles. Okay, so it means we need to develop that. The interesting part is that if we start to develop a plasma catalyzed process, plasma only requires electrical energy input and not thermal energy input. And then of course we have electrochemical processes and electrochemical processes. A very common example being water electrolysis to produce hydrogen. But the same principle can be applied to reforming, for instance, for people in chemical engineering, I'm sure you completely understand what I'm saying. So, and reforming processes can be electrified by transitioning from the current thermocatalytic process to either a plasma catalyzed process or an electrochemical process. The last one there is electrical drivetrain for vehicles or for aircraft or for shipping vessels. So we want to move from ICNG, mechanical engineers is what I'm talking about. We want to move from ICNG to electrical drivetrain. Okay? We want to move from ICNG. Last year, the project led by myself launched the first battery substation deployed in Adamawa State, August 2023. And this program is, that project is intended to, thank you, that project is intended to help accelerate the use of electric bicycles, motorcycles across Nigeria. It's already taken off in Adamawa State and hopefully will come down very soon. Then the next thing is decentralized. Remember the first one we are talking about decarbonize. The second pillar of energy transition, we are talking about electrify. And the next one is decentralized. We want to move away from large traditional generating sources. And why do we want that? We want that for resilience. We want that for transport efficiency, loss mitigation, for people from electrical energy, power systems engineering. Our sound together is no longer part of Seet. Sounded very strange to me. Okay, yeah, but people from power systems background, you understand by transforming high voltage, you can kill losses, okay? And we can avoid that if we take a more decentralized approach to the grid system. So instead of having a big national grid, we can have small grids here and there. Okay, so distributed energy systems, build microgrids, etc. The last point is digitize. So the last pillar of energy transition is digitize. So we want to be able to use AI. Okay, we want to be able to use AI and other digital technologies to digitize how energy is produced and used. And there are a number of digital technologies that are already on trial worldwide. Okay, one of them is what is called virtual power plants. Talk about that in a bit. Smart grid, peer-to-peer power trading, building strategies for electricity retailing. I will speak a bit more about it in a bit. Now, this is where I'm sure we all want to hear more about, and that today does not have any plan to integrate renewable energy system. And that is for a number of reasons. One of them being because the evidence is to integrate it in the grid, and the grid is not robust enough to manage the variabilities. You are going to experience grid collapse every now and then. Okay? It's said that we are very used to grid collapse in Nigeria. But yeah, this is what can happen if you do that. Okay? So it impacts grid integrity. Alright? In the UK, we have a situation where the country has invested quite a lot in renewable energy. But this renewable energy, they are only able to export around 30% of the total renewable energy that is produced across the country. The implication is that the companies that produce the renewable energy are there, government is giving them money not to supply to the grid. You know, you can imagine that. And the technical term for that is what we call energy shortage. So government is essentially giving you money and say, please don't put any energy into the grid. Okay? Don't put energy into the grid. In the UK, as of last count, the cost of energy shortage in the UK, specifically for wind farms, wind power, is already exceeded £1 billion in 1 year alone. Okay? So it's a big deal. When we come to integrating renewable energy. The other point is that most of the times, the places that renewable energy are vastly available are often very far away from where the end users are located. Okay, so what that means is that you have vast amount of renewable energy, for instance, in the desert or far in the sea. Okay, that means after producing them, you need to transport them back, and lots of losses to keep in between. You know, completely defeating the objective of producing those energy. One way that this is being addressed is to go back to kind of turn our heads around. I'm sure all of us have physics background. And what we were taught in physics is that we can talk about electricity as AC as opposed to DC. Now, a new class of materials, material engineering students or academics, a new class of materials that are called the high voltage direct current materials have now emerged that allows the transport of direct current with minimal losses, with better efficiency, more than AC current. And this is where engineers come. So what must engineers do? What engineers do here is to develop energy storage technologies. If we are going to be integrating renewable energy into the grid, we need to develop energy storage technologies. Okay? We need to develop energy storage technologies so that the excess electricity can be stored when it is produced, and when it is needed, we can then take it from the energy storage system. I know your mind quickly goes to battery. But for grid integration projects, you need an awful lot of battery capacity, to be able to use at that scale. That then makes the use of battery storage extremely expensive, for these scales. Right. So the other point is carbon capture and storage. I've already read one of the keynote speeches from Arian and why he was talking about carbon capture and storage, which is beautiful to see. Carbon capture and storage is extremely energy intensive. On average, you need around 4 gigajoules of energy to capture 1 ton of CO2. That's pretty good. The other point is that this doesn't get spoken of a lot of the time, is that carbon capture and storage comes with an economic liability because we are going to be pumping CO2 into the ground. We are going to be pumping CO2 into the ground. Who is going to be responsible for the lifetime cost of the CO2? Oh, NEPA has gone. Okay. Right. So yeah. So carry on. So the big problem about carbon capture and storage that doesn't get spoken of a lot of the time is that the CO2 that they're going to store on the ground, government will continue to take over the cost of that. That is the only way investing in this technology will make sense for companies. All right? That economic liability is part of the reasons why carbon capture hasn't really taken flight as people expect it to do. Myself, who is like a young guy compared to the people that are sitting before us, They just started not long ago. And I'm already counting 15 years working on carbon capture. And the story hasn't changed. It's lots of fancy words, lots of big grammars, and nothing actually working out in reality. And I can tell you that part of the reasons why is because of this particular thing. So what engineers are doing is develop more energy efficient solvent or absorbent materials, is to find ways to transform the CO2 that we have captured into useful products. And the common one is usually looking for, but this is not very efficient. And chemical engineers and people from chemistry backgrounds, for instance, are working on different types of solvents, different types of materials that can surpass forest capacities that we have in existence. The next one is still talking about decarbonize, is developing new fuel. In developing new fuel, I'm talking about hydrogen because hydrogen is the most promising new fuel. Hydrogen transport and storage presents significant problems. Okay? Hydrogen is like the tiniest molecule, as you know, tiniest molecule out there. What it means is that it's quite difficult to store hydrogen. So if you put hydrogen in the same storage tank, you put, for instance, ammonia. Hydrogen will escape, right? It will escape from the walls of the vessel and diffuse out of it. That's because of the nature of the molecules of hydrogen. So I'll speak more in the case studies about this. So engineers are looking at developing area materials for hydrogen, looking at new materials for storing hydrogen to avoid leakages, new materials that can withstand high combustion temperature for hydrogen, and then of course looking at how hydrogen combustion will impact on product quality. So for instance, if you want to replace hydrogen, if you want to replace the use of we have a project that we work with ceramic company, and the ceramic company is currently using natural gas in their kiln, okay? And the question was to transition to hydrogen, and they found that in the trial runs that they did, if they use hydrogen only for their combustion, it then affects the quality of the ceramic products that's coming out from their kiln. So they don't have the same quality. And those are some of the questions that engineers need to try to solve on continuous basis. Last one is efficiency improvement. I mentioned ultra-supercritical power plants and how they are extremely efficient, but they present significant challenges. Okay, so these ultra-supercritical power plants, apart from the fact that you need to develop new materials that can withstand this sort of conditions that I mentioned, around 700 degrees temperature, up to 38 megapascals in pressure, you need to use different types of materials to build the boilers. Okay? So apart from developing those types of materials, you find that this type of boilers are one-screw boilers. The traditional type of boilers that we use in the industry, we usually have a steam drum where the steam comes in and gets separated, so any water that water vapor that is in the steam can be taken out. And it also forms a buffer within the system. Now, allow me chemical engineers. So, the benefit of having this sort of buffer in the boiler, especially the power plant boiler, is that it allows the power plant to be operated in what is called load-following mode. Load-following mode means that the power plant can be turned up. Okay, so if demand is high, you can move from 75% output to say 90% output. And when demand is low, you can move from 90% back to 75 as the text may be. Okay? So that's what we call load following mode. The other option for power plant operation is what we call base load operation. Base load operation means that you are operating at a fixed output, often close to the maximum output for your plant. Okay? So why you can do that with traditional subcritical boilers, which are equipped with a steam drum, you cannot do that with ultra-supercritical power plants because they do not have steam drum. Okay? And that is why they are often called the one-screw boilers. You cannot use them in load-following configuration. You can only operate them in base load. And this doesn't align with energy transition strategies. Energy transition is looking at flexible systems that can be manipulated from time to time to meet specific demands, okay, without losing efficiency. Okay, so that's the challenge. And then, of course, talk about electrify and saying that we want to transition reactors that are common, that are currently thermally operated. So you can imagine thermally heated reactors now moving and becoming electrically heated reactors or becoming microwave heated reactors. That presents a lot of challenges, okay? Because, and then of course I spoke about the chemical and plasma catalytic processes, which following non-traditional chemocatalysis and require new skills in their design. I already mentioned that plasma catalysis follows a different type of thermodynamics that is very different from everything that we have learned, everything that we know as a chemical engineer, for instance. The reactions are completely different, and that means that for an engineering perspective, a chemical engineering perspective, that means that we need to develop new skills. We need to work with people from plasma chemistry, people from chemistry, natural sciences, to understand plasma catalysis, for instance. And that is the only way that we'll be able to develop and design systems for plasma catalysis, for instance. And the same thing applies to electrical engineering, for instance. And in our own university and in many universities worldwide, we now have a subject called electrical engineering that did not exist 20 years ago, and did not exist probably when we were trained as chemical engineers. But now exists because it's become a critical energy transition tool. Okay, now it's and to make the people that we are training to be ready for the future, to be able to play a role in the emerging energy transition space, we need to equip them with the right skills now. We need to go beyond the traditional thermal processes and move on to plasma catalysis, electrochemical engineering, microwave heating, etc. Of course, the last point is electric drivetrain. Okay, so as I mentioned, this is different from traditional IC engine vehicles, or in the case of aircraft, the jet propulsion system. So, and as a result of this, because of electric drivetrain development, there is now a cross-cutting discipline between mechanical engineering and electrical engineering. And this cross-cutting discipline that has emerged as a result is being embedded. You are creating a subject that lies between these two areas. Okay? And this is how mechanical engineers, people in automotive options, I don't know how it's structured these days, but mechanical engineering during our time used to have an automotive option. And people in automotive option can't just be taught the traditional IC engines anymore alone. You have to be able to also bring in electrical drivetrain system, because it is likely going to dominate that space in the future. Right, so, and then lastly, talk about decentralized and digitized. So, what we have in Nigeria currently, like what is being constructed in Futo here, is you have islanded microgrids without interconnection. So, you have a microgrid in Futo, maybe you have another one in Insu, for instance. You have another one somewhere, you have another one. So, we call them islanded microgrids because they are not interconnected for several any outside grids. Okay? And the point is that by building the microgrids without any sort of interconnection, it kind of takes away the opportunity to fully maximize the potential of these systems. Alright? As it is in Nigeria today, without the generous grants that is coming through from World Bank, we find that this development will be very expensive, and most of the people will not be able to afford it. But one way that this can be addressed is to interconnect the grids. Why it's important that we interconnect the grids is because by interconnecting the grids, you will be able to do demand matching. So in some situations, maybe you have a house here in Futo, but every weekend you are somewhere in your village in Umar, for instance. Okay? And during those 2 days that you are away, the energy that would have been produced by your system will go to waste, essentially. Alright? By interconnecting with another subgrid, what will happen is that the system is able to detect that scenario. And once the system picks up that scenario, the unused energy from your house can be shipped over to the people that need it. And you then get money for selling the energy that is produced from your own system. And that kind of subsidizes the cost for everyone, including yourself. Alright? And that is part of what is called virtual power plants. So virtual power plants, we have digital tools that can be used to build a dashboard that tries to interconnect different islanded microgrids and is able to walk through the system and match demands, demand and supply. And by matching demand and supply, somebody in Idiaba can be supplied with some energy when you see that there is excess here and vice versa. Okay? And the other point is power building techniques. This is a different version of the project, but power building has to do with how the people that produce electricity auction it to the discos, for instance, how they sell it to the discos. It is not very significant in Nigeria because our grid is small. But what happens is that imagine that we have our demand. Let's assume that the demand of Nigeria is, let me say, 40 gig. Okay? 40 gig. Let's say our demand today is 40 gig of power, but we have capacity to produce 100 gig. Okay? So how do you match it and make sure that at all times there is profit to the people that are actually investing in that volume? And all that is part of what we have in building strategies and how different companies can be sourced to supply power to the grid, etc. And that kind of system can be developed using AI system, and there are people that are using blockchain, which we know from crypto trading, using blockchain to do the power purchase agreement, and that is making it a lot more efficient. And this means that as engineers, even though we are not supposed to become software engineers, we must become aware of this. Okay? The other point is power sharing and power trading. I've already given an example of what that means. Power sharing, where you have an estate, you live in this estate, but sometimes you are there, sometimes you are not there. And then the energy that you produce that you don't need when you are not there, can be sold to the people that need it, and then you get money for it. So power trading, power sharing, so all of these involve the use of different digital techniques. And one thing that engineers must embrace has to be the use of different digital techniques to deliver this type of task. Let me mention cybersecurity. In the UK, for instance, the ITME now makes it compulsory for chemical engineering programs to be able to provide some background for chemical engineering students in cybersecurity. We are not trying to train them to become cybersecurity experts, but they will understand what cybersecurity means to your control systems. For instance, when you have a system that connects to the internet and you have all that stuff, that means if somebody hacks the system, the person can misalign your control system and you have complete catastrophe for your hand. Alright? So as chemical engineers or as engineers generally, you need to understand this because you're not working with systems that are founded with IoT systems, internet and stuff. And those kind of systems are always prone to cyber attack. Right? So, the non-chemical engineers and even ourselves and the much older engineers needs to get into that space, needs to have some sort of digital skills, going forward to be able to fully get into the space of energy transition. Right, so some general areas where you have some of these roles is taking economic analysis. There's a lot that I can say there, but let's leave it there for now. And then you have sustainability analysis. Sustainability using life cycle analysis is a must these days. Whatever technology that you are developing, at some point you need to be able to demonstrate the sustainability credential of your technology. So it doesn't matter whether you are from mechanical engineering and you are trying to develop you need to be able to demonstrate the credential, the sustainability credential of the technology you are developing. And to do that, you need to be able to do life cycle analysis for your system. So it's not just something for people in the computer science. It's something that everybody in engineering should be able to own. So long as you remain in that space where you want to be able to develop technologies or inform the development of technologies. Right, so I have some case studies. This is just stuff that I have put, and I will run through it very quickly. Sorry for taking your time. So we have a lot of projects that we are doing on hydrogen transportation, and I wanted to talk you through it a little bit. And that kind of gives you an idea of how myself as an engineer is actually using some of the things I was talking about in my own work, okay, and the students I work with me. Right, so hydrogen have very high energy density, higher than most fuels in terms of mass density. In terms of volume density, it's very low, okay? And of course, hydrogen produces only water, it doesn't produce CO2. So those are the things that make hydrogen a very good alternative fuel, okay? But hydrogen needs to come from low carbon sources. There are some figures here that shows you the volume density of hydrogen is very low, you can see here. But the gravitational density is quite high. Okay? And also, you would have found that they use different color coding for hydrogen. And this is just based on where the hydrogen has come from. So you hear about green hydrogen, so which is hydrogen that's coming from electrolysis, for instance, gray hydrogen, blue hydrogen, and the rest of them. You have that chart here. So when you get the slide, you can have a look at that. And worldwide, many countries already have hydrogen strategy in place. In the UK, we have a hydrogen strategy. We have hydrogen filling stations already in operations in the UK. In China, they have an awful amount of targets to reach by the end of this year. And the use of hydrogen as a fuel is not new. Saturn V rocket, which is the rocket that took Armstrong to the moon in 1968, one of the rocket stages, the rocket had 3 stages, and one of the rocket stages was fully run by hydrogen. Okay, so the use of hydrogen fuel is not new. 1950s, 1960s, there has been vehicles that was running on hydrogen. What is different now? What is different now? People are using this in 1960s. What is different now? What is different now is that we now want to build an ecosystem. We now want to build an ecosystem that is entirely powered by hydrogen. And that is what is being referred to as the hydrogen economy. We now want an ecosystem of energy system that is entirely run by hydrogen. Okay? Alright, so the developments of hydrogen economy are focused more on hydrogen production. But for us, we understand the challenges that transporting and storing hydrogen presents, and most of my work focuses on hydrogen transport and storage. What are the problems with hydrogen transport and storage? Now, hydrogen has a very low volumetric density. As mentioned, the smallest molecule that you know out there. So the volumetric energy density is very low. To put it in perspective, when you compare it, like for like, the same energy capacity with diesel, for instance, that of hydrogen is 6 times smaller, which means if you need to transport the same amount of energy that you transport with 1 liter of diesel, you need a volume space that is 6 times that of diesel. Alright? So that means if you wanted to build shipping vessels to transport hydrogen, they will be a lot bigger, or you will be doing a lot more juice in between. Thank you. Alright? The other point is that compressed hydrogen, as I mentioned to you, diffuses through most materials. And when this happens, they tend to embrace those materials. And the worst of them is steel, which ironically is the most used material in the industry for building this type of vessels. So hydrogen embraces steel, which presents significant problems. There is increased social risk, and there is high leakage potential, which kind of plays down on the global warming potential of hydrogen. Right, so currently we have a vehicle that is called Toyota Mirai. It's produced by Toyota. The vehicle is called Mirai. And Mirai has a capacity for 5 kg of 700 bar. Like, you understand? If a pressure of 10 bar is released in each room, all of us here will be in serious trouble. 10 bar of pressure. And then you have 700 bar of pressure. Okay? And how many people want to sit in this type of car? People are already crying because of CNG. CNG is like child's play when you compare it to this capacity. Alright? Okay? Alright, so that's the problem with that. And then we talked about, we looked at, okay, we first of all, one of the first project we looked at, okay, transporting hydrogen as hydrogen, but instead of compressed hydrogen, using the liquid hydrogen. The liquid hydrogen is slightly better than compressed hydrogen. But compressed hydrogen, liquid hydrogen still has some problem because you need to operate at cryogenic temperature. Temperature of minus 253 degrees C. Okay? And the other alternative is to transport hydrogen using derivatives, and ammonia being one of them. Alright? So there are different types of derivatives which are outlined here, just one of. And this figure here is showing you different types of derivatives and showing you that of all the derivatives that are currently available, ammonia is the part. So you can see ammonia that are several. Alright? In terms of energy efficiency, because if you are using a derivative, you need to be able to crack the derivative to recover your hydrogen. And again, in terms of the energy required to do that, ammonia is still pretty decent, compared to many of them. Alright, so the case study, one of them is looking at energy analysis for technologies for hydrogen liquefaction, and the other one is looking at analysis of decentralized and decentralized ammonia to hydrogen network. So, liquid hydrogen has a high boil-off rate, up to 5% daily. Okay, making this liquefaction and long-term storage inefficient. I'll give you an example. So, if you have LNG, which we are familiar with, LNG has a boil-off rate of less than 0.4% thereabout. If you compare it to hydrogen, hydrogen has close to 15. That means if you store hydrogen here and probably don't do anything, you don't do any liquefaction, after a few days, you would have lost the entire hydrogen that you store, the entire liquid hydrogen that you store. And chemical engineers have big role in this, massive space for chemical engineers. If you have interest, I'm happy to chat with you after. Alright, so I'll just try to wrap up now. So hydrogen are also two forms, and the auto hydrogen and the para hydrogen are just trying to run off. So we have a paper that we published some of this, and it's also available on the slide. As I said, the slide is going to be available for you, and you can look up the paper and read a bit more about the hydrogen liquefaction. The other one was looking at, this is a figure, the figure I was talking about, high boil-off rate. So for LNG, the boil-off rate is 0.015, okay? And that of hydrogen is as much as 5 volume percent per day. Okay, so if you have 5 volume percent per day, that means within a space of 20 days, you will have lost everything. 20 days. Okay? Alright? And this is why there is movement towards ammonia as the main vehicle for transporting and storing hydrogen. Alright? So we did a lot of analysis, looked at existing ammonia infrastructure worldwide and what already exists there. So we did all that analysis. Again, this is also published somewhere. I'm so sorry, the laptop has gone off functionally. Yeah, so the slide is available here. Some of this has been published, and if you look up the slide, you'll be able to find these papers. Ammonia is a very strategic component within the hydrogen economy. And our project has looked at the UK and analyzed the hydrogen supply to heavy industrial end users across the United Kingdom. So we did some analysis to work with Air Liquid, because Air Liquid is trying to build a landing platform for imported ammonia in the UK. So from the landing point of Air Liquid in the UK, our assessment looks at how this can deliver to various end users. Okay?
seat. You can have your seat. As you were speaking, something was just ringing a bell in my mind. There is need for Moses to upskill. I don't know about you. I don't know about you. I'm talking about myself. So I understand that as an engineer now, the essence of getting digital skills is now very, very important. And the need for collaboration is also something that we have emphasized. I know some of us will have one or two questions to ask. We have such questions because the lecturer said he had 10 questions. Okay? After counting, we will not give you the mic. So let's get the number now so that we can allot time. Okay, we have
For the wonderful lecture. But I have been having issues with underground carbon storage, especially in a climate like Nigeria, where people drink at random. Other places, it could be fine, but here, people looking for water, looking for so many things. Is this safe here? Thank you very much. Engineer Samuel. Carbon storage, underground carbon storage.
Underground carbon storage. Well, the carbon storage it doesn't get stored anywhere. It's often in disused oil and gas wells. Okay, and such places is not where people dig around for just an aspect. And the depth that you're also talking about is not a depth that you will just dig and you stumble on it. Then the other point is that if carbon has been stored in a specific area, that area becomes a place that will have to be monitored for the lifetime of the well. Alright, so it cannot then be a place where anybody can just go and study. So yeah, it's completely safe in Nigeria. And I think LNG and NNPC is already doing some prospecting offshore for potential carbon storage sites. Yeah?
Yes, and my name is Mr. Estebo. I heard when you said that one of the pillars of energy transition is to decentralize. And if we are trying to pay for traditional generating sources for the sake of resilience, again, coming to the challenge or challenges, you also said that there is a need to make island microgrids to have interconnections of sorts for optimal performance. Is that not kind of getting back to centralization? That's one of my things.
Obviously, when we are talking about decentralized, we are not essentially saying that there will not be the major network grids. There will still be the major network grid. What will be different is that you now have sub-grids that can be disconnected from the main grid. Okay? And so if there is collapse in one of the sub-grids, you will not have the national collapse like currently. Okay? So there will still be the main network grid, but the role will then be slightly different from what the roles are today. Don't know if it makes sense.
Yes.
Yeah?
Yes. The other one is a concern for safety. Since we are trying to move over to hydrogen-powered energy sources, energy use or whatever, is there any effort being made to also curb the development of hydrogen weapons, that like hydrogen bombs and all the rest? Because if we eventually get to that point where everything is now being powered by hydrogen, and somebody decides to unleash on us something that is hydrogen, hydrogen bomb or something like that, wouldn't that lead to a massive global catastrophe kind of?
Well, first of all, something like security is government thing. It's not for us as engineers. Ours is to be able to find a solution. But yes, energy assets are national infrastructure assets. You cannot just walk into a place where you have, for instance, a gas-fired power plant, because there is also potential for such hazards there. But you cannot just have access to it. Okay? If you do, you will be trespassing. Right?
Yes, I'm going to talk about networks. In your experience, what is the most overlooked technical challenge in scaling up carbon capture systems?
I think, I'm not sure whether the right word will be overlooked, because like it's looking at us and we are looking at it. It's not that anybody is overlooking it. But the main problem why people are not very confident, I tell you, is that the cost that will be passed down to end users. Some scenario models say that if we integrate carbon capture systems to our existing, for instance, natural gas power systems, that it will increase electricity prices by, give or take, 80%. And the people that are going to be responsible for paying that is going to be near the electricity end users. And this is not something that the government is willing to see happen at the moment. We believe that's part of the problems why there is the hesitance in fully adopting carbon capture in the electricity market. Okay? And that's why the more attractive solution is to look at technologies that convert CO2 to different products, kind of generating income for the companies investing in it, so that if that is to be the case, government will not need to be subsidizing the technology. Okay, government will not need to be subsidizing technology, and the company will not need to pass down costs to end users. And for that aspect of development is new. It's emerging, kind of. But what is not emerging is using the capture CO2 for EOR, petroleum engineering students, academics here understand that. Enhanced oil recovery. So there are already projects that is using captured CO2 to enhance oil recovery.
You know, in this energy transition, there are critical minerals, and they're all abundant in Africa. Cobalt, nickel, lithium, copper, and even the rare earth metals. Is there any cost to you can advise our team to introducing Seet to help us harness those minerals?
Let me tell you what obtains in Europe. In Europe, we had a major European grant application that we lost because they said we were focusing on, they call it critical raw materials. They are critical raw materials because those materials will potentially run out at some point. And this is part of the reasons that technologies that involve the use of critical raw materials are usually kind of played down in favor of technologies that do not. Alright? As for subjects that can be introduced, I don't know how the curriculum system works these days in Futo, but I know that the curriculum in Nigeria seems to be controlled by NUC. Don't know if I'm right. Yeah, so if it is controlled by NUC, that means that Futo cannot just wake up and start creating programs. But what can happen is that you could have projects that focus on different critical mineral extraction projects. We have a project with a company in Lagos that is looking at extracting lead from lead acid batteries. You know, lead acid battery, the one that's completely dead and ready to be thrown away. And so you could extract the leads there and aggregate the leads and actually sell it. Okay? And there are already technologies for doing that in the market, and what we are doing is just to look at more sustainable ways for doing that to avoid lead poisoning and whatnot. So in our chemical engineering program, we could in principle have critical raw material recovery technologies as part of the things that can be taught within the separation processes model. Okay, so the separation processes model, Professor Ken, may God rest his soul, used to teach us separation processes back in the days in Futo. And this kind of subject can be embedded within such course. And there are already separation processes that are not entirely strange for people in chemical engineering, for instance. And also people in materials and metallurgical can also embed some of them. Okay, so two departments that can embed that, chemical engineering and mathematics. I don't know if it's possible.
Christian Oachi. And the question I want to ask is regarding the use of ammonia as you call it a vehicle for hydrogen tech. So I know that the cracking process that leads to production of hydrogen is an endothermic process, and that will require a lot of increase in temperature. So I want to know, does it really subsidize or minimizes the energy losses during production process, since you have high temperature need for you to be able to crack out hydrogen from ammonia?
Yeah, for chemistry, right?
Yes.
Okay. All right. So the interest in ammonia is for long distance transport. So let us say that in the UK has plans to import hydrogen all the way from Australia, for instance, and Middle East. Now, our own studies shows that if we produce hydrogen, if hydrogen is produced there, cheap hydrogen, and then transported to the UK, the cost of doing that is very high. But it's not just the cost, it's also the technology readiness for doing that. Okay? The technology for doing that at scale is not ready, it's not there yet. Okay? But the technology for transporting ammonia is there. Well established, well understood, and you have people in the industry that have significant experience in this area. So it's about using what already exists, especially because many countries have set these very big targets, some of them unachievable, by 2030, which is just 5 years down the line. And they say the technologies for transporting hydrogen will start maturing from 2035. Okay? So if you want to wait for the technology for transporting hydrogen, that means you cannot meet your 2030 target. It's very simple. Do you understand? So it is not just about the energy savings, it's also about technology readiness for this transport to happen. Okay?
Yeah. Sir, Doc, I am thinking that because you didn't mention technology that is also going on now, a shift from storage and distribution of hydrogen, because that's a very huge problem that we have, storing and distributing hydrogen. First, hydrogen has a very low calorific value of 10.88 megajoule per meter cube. When we are looking at what we have already in the UK, because that's what we are currently working in my school in Cranfield. So we are looking at biomethanation process. The one that is being used in Germany through superficial reaction. That one is, of course, at 500 bar and about 700 degrees centigrade. So we are looking at biomethanation, where you can convert the green hydrogen to methane. Burning methane produces only one molecule of hydrogen. Now, how do we get it back into the system? We develop another system called ex situ biomethanation process, whereby you can use through carbon capture. That's what I've been laughing here when you are talking about carbon capture. Because I'm looking at that carbon capture is the way to go as it is. If we get a carbon capture through that ex situ biomethanation process, now we can use that carbon dioxide, inject it into a system that can be reduced through hydrogenotropic methanogen. And that's a sustainable approach where you use bacteria to do what? To act on the green hydrogen and then reduce it back to methane that can be used. Methane already has 35.8 megajoule per meter cube. So I want you to look at that aspect, because I'm not looking at the superficial reaction, because that's not sustainable. You are talking about sustainability, that's just what you said. So ex situ biomethanation, I think is the way to go for now.
I'm not sure I completely understood you, but it didn't sound like you were asking a question. There are lots of technologies that can be used, okay, on paper. But the big question that you will be asked if you were making this presentation before business executives is, what is the technology readiness level of this technology, of the technology you just mentioned? If an investor is here to bring the money, what is the technology readiness? And the investor is interested in a technology that is technology readiness level 9. The technology you mentioned is barely technology readiness level 5 as of today. Okay? It's barely technology readiness level 5 or 6 thereabout. Okay? So most of the times it depends whether you want to focus primarily on the fundamental aspects and look at those emerging areas and looking to start developing pilot systems that can be used to further validate the emerging areas. The other point is that you may also want to think about the market-ready solutions. The UK want to cut emission by almost 30% in 2030. Will that technology be matured enough by 2030 to be able to deliver that objective? And the answer is going to be a resounding no. Okay? So yes, and this is why the UK is exploring more market-ready solutions. I was lucky to be invited to an innovative project for Ukraine. And the UK government is ready to give big money to anybody that comes forward with market-ready solutions that can help Ukraine to address the current energy crisis in their country. Okay? So you imagine that. So when it comes to that point, it is not the talk that is it is not the big sounding words. It's not the big sounding technical words that will cut the shades. What's going to make the difference is that you can actually put out evidence that this technology has been tested in comparable industrial environments, and that there are now some of such technologies that are already out there in place in operations. Okay? Carbon capture is never out of the equation. I just believe that worldwide, in many countries, the UK is the worst, that the government doesn't quite have the courage to give the go-ahead for carbon capture. And that's the reality. The UK government has invested for over 30 years on carbon capture, and yet they've not had the courage to give green light to building large-scale, commercial-scale kind of carbon capture systems. Okay, so that's the reality. Canada has done it, Middle East has done it, China has done it, US has done it, but the UK has not managed to pull it off. The entire Europe has not managed to do it. What you can find across Europe and across the UK are very small-scale equivalents of carbon capture systems. And that's the problem for the kind of proposal that we have. What the UK wants to do instead is that they go to Middle East, they go to Australia, places where they can produce low carbon ammonia, import it, bring it to UK, and when it lands in the UK, they will crack it, produce hydrogen, and supply it to the end users. That seems to be like a market-ready solution. If they put out the money today, the technology will be running before the end of the year. At scale. Okay? Yeah, so it is what it is. But on our side as academics, as researchers, it's interesting to be able to query some of this and continue to develop our own skills, deepen our own understandings, and be able to have the sort of conversation that we are having about this, about the technologies. Okay? Thank you.
I think you have enlightened us on this about energy transitions. I just want to find out, because you have mentioned the hydrogen gas as the way to go also. I want to find out, we're all gathered here. I want to find out, do we have opportunities to produce hydrogen in this country? So that one of the takeaways is that we just go home and start looking for how we can produce hydrogen here, so that we don't fall into the trap of now trying to import hydrogen. Then secondly, the challenge of transportation of hydrogen. You have also reminded us that hydrogen is a very low molecular element. That even steel, alright, you can even turn steel as a storage material. So my question is, what type of material is very suitable for storing and transportation of hydrogen? Thank you.
In terms of the material, so you have new class of materials. They are called carbon fiber reinforced materials. Those carbon fiber reinforced materials is made with carbon fiber, which is a very expensive material. So those type of materials are suitable for transporting hydrogen. But because the material itself is very expensive and very energy intensive to make, the process of making carbon fiber, you have some part of the process that operates at temperatures over 3,000 degrees C, and that gives you an idea of the sort of energy intensity that is required for this process. So that means while it has been possible to build very small scale versions of such vessels, it has not been possible to do very large ones, which is what you require for large scale. But the material now exists and can be used for storing hydrogen. What people want to do is to look for alternatives, look for ways to drive down the cost of those materials before going to full-scale production. Okay? And there are companies that do that in Europe and China currently. Then the next question is whether there is potential for us to make hydrogen. 100% there is. By the way, you know the Warri Refinery and Petrochemical Company. So the Warri Refinery and Petrochemical Company is supposed to be a refinery and a petrochemical company. Now, one of the reasons why the petrochemical part of that establishment has not managed to function is because it requires hydrogen. And when the refinery that is supposed to be supplying hydrogen was not working and has not been working for ages, that part of the establishment also died off. And the only solution was to import hydrogen, but then that presents all the issues that I discussed with transporting hydrogen as well. Okay, so yeah, it's impossible. It's possible to produce hydrogen because we have refineries, and hydrogen can be made from the refinery. In principle, this will not be the type of clean hydrogen we are talking about, but it can be made here. If those processes, the refinery processes, can be integrated with, for instance, carbon capture process, then we can make that hydrogen clean, and that hydrogen can become what is called blue hydrogen, because the associated carbon emission has been taken out of the system. So we can make it. Then, at very small scale, anywhere you have water, you can make hydrogen, in principle. Anywhere you have fresh water, you can make hydrogen, and you have small scale electrolyzers, that you can buy, plug to power, put water in there, add some caustic to it, and allow it to run for a few hours, and you will have hydrogen, in principle. What can then become debated is that the amount of hydrogen you produce from that is quite small and may not be very attractive for very large scale production. But for the purposes of teaching, for the purposes of demonstration, for the purposes of showing that it's possible, yes, it is possible, and the students can even do that as a project to produce miniature electrolyzer systems which can actually function. Some of the research that I do with some of my colleagues is looking at new catalyst materials that can be used to enhance the performance of that system.
It's been an intellectual stimulating, and we'll keep talking and keep answering. At the point I was saying, will you be able to answer all the questions? And as he keeps answering, he keeps keeps revealing new dimensions that are also bringing up more questions. Yes, that is how academic conferences do that. And I'm happy we are starting on a very good footing. A lot of applause for everyone of us here present, because the takeaways are there. The takeaways are everywhere. And I could see a lot of people jotting down something. The undergraduate and master's degree project that will be coming from Futo, concept of this exercise is something I am waiting to see, because our minds have been activated. Thank you, Dr. once again for such an interesting session. I think the dean will come with the guest lecturer with other members of the high table for a photograph, after which they will be joined by all the professors here present, and then every participant will not have a shot with our guest lecturer, who incidentally was sometime over 2 decades ago here as an undergraduate. And I tell you, in this university, players are invited people, and this is what we are experiencing here this afternoon. Thank you very much, thank you very much. So it's time for photograph. When we are done with the photographs, we shall all proceed to the AC Fuel Center. I wish we had a collaboration with them for them to be part of what we are doing, because it's all about energy, energy, and energy. Okay, the photographer, are you ready? Okay, every other participant, please join. I think we shall all be here for the second technical session, so that we can all take our lunch together before we graduate into the technical session. While that is ongoing, the certificates of participation are ready for those who registered for the conference between the date of announcement and yesterday evening. But if you registered this morning, your certificate will come later. So therefore, within these 10-15 minutes, let us not rush there. You can on your own, if you decide, you go approach the institution desk and they will attend to you and give you your certificate.
We'll allow every presenter to present their works. So if you have any question for each of them, you write down the question. So once we are done, we begin our questions and we call them up one after the other. That is to help us save our time. Thank you.
On the use of bamboo bombs or sand as reinforcement materials in concrete. The rapid increase in the world population has created the corresponding increase in the size for shelter, and also the great need for shelter buildings and other social infrastructures has equally created a high demand for the key construction materials, which are steel and concrete. And concrete is very strong in compression, but weak in tension. Also, steel is very strong in tension, while weak in compression. So, because of that, steel and concrete are being used together so that steel will provide the tensile strength required in structural members. Now, because of this high demand for these two construction materials, especially steel, as we are discussing, the process of manufacturing of steel produces enormous carbon dioxide emission to the atmosphere, and as a result, it also contributes combustion of fossil fuels. So it's energy consuming. So as a result, steel is very expensive and it causes a lot of environmental and health hazards. So as a result, scientists and engineers are in serious search for cheaper and eco-friendly and sustainable construction materials which can provide tensile strength required in concrete members. And among these materials, one that has been found to be of use is bamboo gum, or we call it bamboo sands. And bamboo is a special material in that it is adjusted to be the fastest growing grass on earth with a growth rate of 91 centimeters per day. And it matures faster than any other wood. It matures within 3 to 5 years. And also the propagation is easy to propagate. You can propagate it by stem, by branches, by rhizomes, or by seeds. So it is an abundant especially in tropical areas which Nigeria belongs to. In fact, in most of the forests in Nigeria, especially in southern Nigeria, it is a natural occurrence here. So we have it in large abundance. And also research has shown that bamboo has high tensile strength, which is approximately the same tensile strength with mine steel, which is about 250 per millimeter strength. So since it has such a high tensile strength, why not use it in concrete member to provide tension needed? And because of this, some of the developing countries like China and India, as you can see in the picture, have already gone far using bamboo. In that picture you can see a reinforcement for beams and tunnels. They use bamboo guns all through as the main reinforcement. The only place they probably seal their wood for the mine seal was to use it as links on the seals. You can use your 6mm or 8mm seal, which is that one cheaper, mine seal, not as seal. But the main important member here are 12 bamboo guns. Even last year, somewhere in Anambra State, I think in either Colombo or Block there's this viral video that I was going to, where they were constructing one solid building, all bamboo as reinforcing member, bamboo guns. So it will go a long way because there is no energy source and it doesn't emit CO2 to the atmosphere, it doesn't involve combustion of fossil fuel, and it doesn't consume much energy, and it is far cheaper than steel. So technology and scientists advise that we go on using bamboo as reinforcing members in concrete. Now, essential treatments are required to bamboo pump to enhance their mechanical properties. Even though these treatments, when given to bamboo pump, it will increase their mechanical properties. But even without these treatments, you can still use them as reinforcing bars. And one of those treatments required is immersion in water to allow to reduce the cellulose content of the sugar, because that sugar attracts ants and insects that brings deterioration. Again, is surface fortification on the surface of the bamboo pump. When they are forgetting, this is contact, mechanical contact with concrete, and increase the bond strength required. Again, you can also provide a waterproof coating using a light bitumen, and also using a pump and sand coating on it, just to provide a rough surface on that on the bamboo pump to increase its bond, and also the provision of the waterproof coating is to prevent shrinkage and swelling of the bamboo pump and certain absorbed oil which causes cracks in concrete. Now, what are the limitations that are used of bamboo pumps and reinforcing bars in concrete spaces? Number one is they pour on with concrete because this surface is smooth and waxy. It doesn't bond well, and to enhance that bond, to enhance this bond with concrete, you congest the surface or you can coat it with sand after applying an epoxy on it. Again, it's also another limitation to it is that bamboo is a combustible material. So while using it in concrete as reinforcement, you need to provide sufficient concrete cover to it so that when there is fire outbreak, not just burn it, but that concrete cover will cover it and prevent it from being burned. Thank you.
Thank you very much. Strong in compression technique intention. He also told us that steel is the opposite. Steels are strong in tension but weak under compression. That's the key takeaway. Now, as a result, there's a particular material that is available in our environment, very abundant, and that is bamboo. And evidence or research outputs have shown that bamboo is as strong as steel. So he was trying to make a case that we should begin to use bamboo in place of steel. Thank you very much for your presentation.
Dr. I.C. Onyechere, we want to bring up another presenter. Do we have W.C. Ulaka? Are you here? Okay. What about Dr. Kingsley Atsome? Are you here? Do we have R. Anthony and Ebe Omoga? They are not here. All right. What about O.M. Idehen and M.S. Wankudu? Are you here? All right. Please let's put our hands together for Dr. O.M. Idehen, and he's going to present towards cost optimization in Nigeria's upstream oil sector, unit operation costs, UOC dynamics, and modeling approaches.
Colleagues and lecturers, professors in the house. So we have before us a topic that relates to cost optimization in the Nigerian oil and gas industry. So we know that the oil and gas industry is the backbone as far as revenue for the country is concerned. Currently, 90% of our foreign exchange is from the oil and gas industry. And the industry is actually subperforming. It's not performing as the government say, considering as far back as 1967, 1970, when crude oil began commercial in the country. So, and what has been backed up is the high unit operating cost. The unit operating cost currently is not competitive compared to our peers within this region of the world and even globally. And that is a key deciding factor for investment in the oil and gas industry. And that is why recently even the president of President Tinubu, he actually gave an executive order promising tax incentive for operators that are able to put in place cost reduction measures. So 20% tax incentive for operators able to put in place cost reduction measures. You can imagine what that would be, for instance, an asset that is producing, let's say $20 per barrel, $20 per day, and factoring for the whole year. You are looking at over close to about $80 million US dollars. So if you now factor in your company income tax and the hydrocarbon tax at 30%, no longer at least. So you are looking at about $60 million as tax. But the president is saying that to motivate operators, because our operating cost, like I said, is on the high side. To motivate operators, 20% of that $60 million is now given as a tax rebate. So that is like what is bringing about more interest in cost optimization. And what is happening during the operating costs? We have the formula there. There are some factors that come into play in terms of your production, logistics, in terms of your regulatory costs, and also your maintenance costs, and also the production itself. But this is a system. As you are controlling one, is an impacting on the other one. There is no one that exists in isolation. So you now discover that looking at this slide, for instance, you discover the next slide is the element for production, for instance, your labor cost, your material cost. You can plan those ones for the year. But when you come to logistics, there is a failure in your right of way, the movement of the hydrocarbon. That's beginning to bring about increase in the unit operating cost, and that's what brings me to this slide. Can you go to the next slide? Dynamics. So if your logistics is flowing normally, your UOC is stable. So there is a relationship there under the time cost behavior. We have both a linear and the exponential relationship. So if your logistics is moving normally, you are looking at the base cost, which is what every operator wants. But we know that in reality that is not the case. So if there is an infraction in your product movement, there becomes a reflection on your unit operating cost, which this functional comes in. And if it is controlled within limits, you can have it linear, which is more preferable. But once it surges, that's where the exponential comes in. And that one can come to maybe by sudden disruption in your flow line. So that's exponential skyrocket your UOC. And that is why we saw that when our pipeline are vandalized, the operators are not smiling at all because you have the whole of the production is still on. They are able to reduce production because there is no evacuation. Your storage is still up already. So the whole essence of all this is how do we now work around the optimization of the unit operating cost. Like we said, it's a system. The production is there, the labor is there, the chemicals that we dose in, maybe our inhibitors, our demulsifiers. How are we sure that we are actually dosing the optimum level? Have we carried out an audit to see what the present state of the plant is? And this is now leading to the last slide that speaks to Internet of Things. That there is need for real-time data monitoring of these assets. Real-time data monitoring, not the one we do maybe time after as the case demand. Real-time data monitoring of the chemicals we are putting, the man-hour, and even the production asset. Because UOC is a dynamic metric, it is not a static metric. And as condition changes, we must have a model in place that is able to take care of the prevailing condition. So advancing investors to Nigerian oil and gas industry will require an optimized UOC, and you agree with me that currently we don't have that. So there is a gap there that needs to be filled. Whatever is not measured can never be managed. So this is the end of the presentation. Now we can have the questions.
The decision of cost optimization was well taken. Of course, we all know that in the oil and gas industry we have the upstream, the midstream, and the downstream sectors. So this is what concentrated on the upstream sector. And of course, we all know that optimization is about putting something to its best use. Now, his analysis was on production costs, regulatory costs, maintenance costs, and the logistics costs. And
we also included that there is need for real-time data monitoring of the chemicals. Thank you so much. OM, now we want to call up G. Bioware, S.A. Adekola, and K.A. Amusa on anatomy of RF exposure at GSM frequency band, SAR calculations in realistic human head SAM models. Are you there?
Really honored to be presenting this today to you. My name is Dr. Rodney Yomi from the Electronic Department of Nigeria Delta University. I'm here to present the anatomy of RF at GSM frequency band. Follow. SAR calculations in realistic human head SAM models. Now, the use of a GSM phone has truly escalated in the world today, and even in Nigeria. So this has caused immense concern amongst the general public. So what we want to know, when you are using the GSM phone on your head? Is it affecting you? What is it causing in your body? People have been asking this. So the research is into this to see what is happening when the signal is entering your head, when the phone is close on your head. And even the mass around us. Some people may say that we are being microwaved because we are in the electromagnetic field. So, in this work, we deal with RF exposure from mobile devices. Then we calculated SAR. SAR is the specific absorption rate, which is a meter that measures the amount of energy the device propagates into your skin tissue. Then this is done with a guide from regulatory bodies like the FCC and the ICNRE. This bodies, they set the standard for SAR absorption into the human body. And in this work, we focused on 4 frequencies. We got in the 700 to 2,600 megahertz. In between, we have 800, 900, and 1.8 gigahertz. Now, there's a standard model that has been created by IEEE, the Institute of Electrical and Electronics Engineers. They created a model called the specific anthropomorphic mannequin. Now this is to mimic the human head. So the dimensions and everything of an adult head. So that when you place a device, like a smartphone on your head and you are making calls, what is happening? What is it? What kind of energy is it projecting into your head? So there are the dimensions. If you go through the computer, then we look at the dielectric properties of that human head, because the frequency determined, the dielectric property is determined by the frequency. If you increase the frequency, something happens. We have the dielectric properties which are permittivity and conductivity of the human tissue. The conductivity tends to increase with frequency, while the permittivity tends to drop with frequency. Now, what we use for the SAR calculation, we did that by calculating using Fritz's transmission equation to calculate the electric field. We're not using a specific device, we're just using the parameters of this device to calculate the electric field. Then use that to calculate the SAR, which we now use to simulate our results. Now, the results, I wish we have it on the slide. We have seen the result. We have 2 graphs. One we call that the heat map. Now, the heat map, what it does? Okay, those are the 2 graphs. One is a bar chart, the other one is an heat map. The heat map, you can see at the bottom there, we have somehow reddish color and transitioning from that to yellow and so on. Now, what this is telling us is that by the time you place the phone on your head, the heat, physically normally you feel the heat of the phone after a while when you're making the call. So you can see that's the heat on your skin. But as the heat travels in your body, that's what is happening. It is cooling down. So by the time you get to that blue section, it has totally cooled down. So you can see that the part of your body, your skin, that's your skin, not even going into your head. The skin is the surface of the skin, which is the structural onion layer on the epidermis. That is what will fill the drop of the heat. But by the time it goes into the skin, just your skin, the length of the skin. If you look at you see 8.5 millimeter there. That is the thickness of the human skin, combining epidermis, dermis, and the subcutaneous part. So as it goes in, the temperature tends to drop. That describes the heat, and that is causing from using the SCR and calculating that. Then the bar chart is to show us the rate of SCR, the frequency. You can see that there are 4 frequencies there: 700 megahertz, 900 megahertz, 1.8 gigahertz, and 2.6 gigahertz. From observation, you can see that. Conclude. Okay, to conclude, you can see that with frequency, we have an increase in the SCR. If you are talking about a specific device, most of these devices come with a specific SCR. And that SCR is used for different frequencies. It's a whole different story. Thank you.
Thank you very much. Whether we are aware that mobile phones have effects on our health or not, the other remains that we conclude these things. We were trying to point out that when we have a mobile phone or any mobile device that generates infrared radiation, that is heat, that eventually is going to affect our brains. So we have to be very, very careful. Also, staying around masks also is a problem. And
so what do we do? Stop using mobile phones? No. I think the solution should be put it on speakers and keep it away from your skin. Alright. We want to invite the next presenter, but this is going to be where's Dr. Yowe? We are calling you back again while we wait for the next presenter. Mobile communication signals in human tissues. A multi-layered analysis using PNS, bioheat, and cocoa models.
Okay.
You get it now?
Yes.
All right.
The next item is assessing thermal effects of mobile communication signals in human tissue. Now, to complete that, we looked at some models, Penn's bioheat equation and the cocoa equation. Now, in the previous presentation, I talked about a similar effect of using GSM signal around us. Now, what we didn't mention there is the multiple layer of the, we didn't consider the multiple layer of the human skin. Here we are considering that. And to consider that, we look at the using what we call cocoa model. The cocoa model models the layers of the skin that is absorbing this energy. What does it do? When we use when we get, in this case, we're not using permittivity or in analyzing the energy absorbed. We're using the complex permittivity. This takes care. Hello. Now, this takes care of the complexity of the human tissue. You know, like I mentioned before, we have 3 commonly used layers. Within that, we have several layers. Like the epidermis has another 5 layers within it. You know, so all these layers have to be considered when you are talking about the energy absorbed, the SARO, and the wave propagating and the heat generated. Now, like I said before, this has always been a concern to everybody. Is this thing killing us? Like I could recall in 2020, there was a rumor that GSM signal was because of COVID-19. Even myself, I was almost believing it until I went deep into research and saw that this wasn't true. You know, when the wave hits your skin, there is reflection. You know, there's scattered wind. So what is entering your tissue is very, very small compared to the wind in the cell. So here we also use the 4 frequencies: 700 megahertz, 900 megahertz, 1.8 gigahertz, and 2.6 gigahertz. So, like I said before, the difference here is we are considering the multiple layers of the skin, not just taking it as a single layer. Here we model the human skin as a multiple layer epidermis and dermis. Applied Coco model for dielectric properties, use Friis equation and tissue impedance to compute SCR. Model temperature rise using Penck's Biorhythm equation. So the results we obtain are summarized in a table. For the 700 megahertz, the conductivity there, according to the frequency, the conductivity there is 0.79 Siemens per meter. Then the Coco value there, which is a complex value, is 41.92 minus J 20.73. Then we have for the penetration depth, you know, the penetration depth, the depth in which that will go into the skin tissue is for 700 is 0.351. You can see, you know, you have the skin tissue to be 8.5 millimeter, but you can see the depth of penetration here is just 0.3451 for 700 megahertz, and the SAR it carries to that point is just 0.1112 watts per kilogram. You know, so those are the values, and these values speak for themselves that this cannot get to the point of causing diseases like COVID-19, according to our research. Now, if we go further and get to the end, you can see that for 2.6 gigahertz, if you compare the SAR with the 700, you see that the SAR has increased. Earlier I mentioned FCC ICNRP standard. FCC gives a 1.6 kilogram watt per kilogram. You know, the 1.6 watt per kilogram standard. So any device produced should not be producing more than that for FCC regulation. Therefore, ICNRP regulation is 2 watt per kilogram. So when we look at all the SAR rules there, you can see that they are all within the standard, and these cannot cause any form of okay. So the next slide is the graph. Now this graph shows the temperature rise in your tissue. You know, if you look at it closely, you see that you started from 6.6 degrees Celsius, and an increase for that for the frequency. You can see how small. If you trace it, you can see that the temperature increase are so minute, so small that it's almost it's not noticeable. That is why there's no way this thing can go into your system and eat up your internal organ, because it cannot even penetrate beyond your skin tissue. So this is the graph. So finally, we using the SAR rule, and we said before, with frequency, the SAR rule increases, and with frequency, the penetration drops.
Thank you once again.
They even went as far as measuring the conductivity of the skin according to frequency. They also measured or computed SAR we were even made to understand that the epidemics has up to 5 layers. Thank you very much for your presentation.
We also talked about the depth of penetration. For using 700 megahertz, he had a depth of 0.3451, and he concluded that this is not enough to have caused COVID-19. Can we put our hands together for him, please? Thank you. Online. And that will be on the topic optimizing biodiesel production from refined castor oil with titanium dioxide, dosed calcium oxide and catalyst using response surface methodology CCD approach. That is central composite design. And to take it up is Dr. W.C. Olakba. That is okay. Can we put our hands together and do what it is? And we have Dr. N.J. Ozlan, utilizing a biopolymer cashew gum extract as corrosion inhibitor for mycel in acid chloride environment. So your time starts.
Okay, mycel, as you know, is a material that is found useful in various applications, industries, storage tanks, pipelines, and then it fits the challenge of corrosion, which will definitely affect the potential of the material for those processes where they are useful. And so this was trying to see how we can get an inhibitor that can help manage the corrosion of mycel than acid and chloride. Alright. Before now, there are prior studies which have shown that plant extracts are useful as corrosion inhibitors. And then this work is also going to use cashew gum extract as that inhibitor. And then we will look at functional components of the gum and also how it will affect mycel to handle the corrosion of the mycel. Alright, we have the materials that are mycel. We have the reagents for acid chloride, which is sodium chloride, sulfuric acid, and acetone, which is used to clean the mycel. And then the mycel is prepared for the experimentation. And then we also use SIR, that's Fourier transform infrared spectroscopy. We use it to find out the functional group present in the cashew gum extract. Now, these functional groups, we discovered that it has a functional group like hydroxyl group and also polar functional group that will absorb to the surface of the mycel and help to prevent the fast corrosion of that mycel sample. And then we also use RSM. This RSM is used to generate a model, and that model is to predict the corrosion inhibition efficiency of the gum at various temperature, various temperature, inhibitor concentration, and time. Okay, from our results, we have the RSM analysis, and the model that fits, next slide, the model that fits these results we have is the quadratic model. Next slide.
The previous one, sorry.
Okay, the quadratic model fits it, and our R-square value is close to 1, and the adjusted R-square value is also close to 1, and it's less than 0.2 in that of the main R-square. And then our equation is equation obtained using design experts, which was used for the RSM analysis. The A, the B, the C, the various variables that we use are represented here as well. And then this result of the XIR analysis that we carried out, the stretching vibration showing the hydrogen present, the peaks at 3,000 to 2,800 per cm, showing the C functional group present. And then the implication of these functional group presence is that they can absorb to the metal surface and help form a protective layer that will reduce corrosion on the vinyl steel. Alright, with this work, we have confirmed that this productive model is accurate to help predict the initial efficiency of cashew gum in acid layer region. And then the gum, as obtained from the XIR analysis, has shown us that functional group presence are necessary and important to help absorb on the mass surface. The last slide, sorry. And then we also have work relevant to the SDG goals, SDG 9, SDG 13, and SDG 12, which are industry, innovation and infrastructure, climate action, responsible consumption and production. So this work is in line with our theme for this conference, which is to help get sustainable and cleaner energy for mass. Alright, acknowledgement. I want to acknowledge the research group, environmental composite and optimization research group, Israel, Sadoki, and the Department of Chemical Engineering, Futo. Okay, these are references for the work. Thank you so much.
Thank you very much. Of course, as engineers, corrosion and easy revision is a very serious topic because still is found everywhere. And of course, to prepare cashew gum, one needs to get a cutlass and slice the cashew tree, right? And the gum will come out. And then you utilize it to do whatever you want to do. They did their work using mild steel and in acid chloride environment. Thank you very much.
I believe we have our questions written down for me. Now we'll be on to our next presenter, online presentation, and that will be R. Anthony and M.A. Onuba.
My name is Engineer Victor Oka. The title of my presentation is Effects of Temporary Heat Treatment on Mechanical Behavior of Medium Carbon Steel. Yesterday, we discussed extensively on resilience engineering. And there is no way we can talk about resilience engineering without talking about value engineering, an aspect of engineering that has to do with improving our design just at the product design stage. So in engineering, in quality engineering, material selection is of essence. And medium carbon steel, which is our major material for consideration in this study, is one of the major materials that are used in almost every aspect of engineering endeavor. So we have that medium carbon steel is carbon steel that has a carbon content within the range of 0.3% to 0.6%. And we consider medium carbon steel because of its balance of strength and toughness in all engineering applications. Then heat treatment is a group of thermal processes that are used to modify the mechanical properties. Thus, we use heat treatment to modify the properties of a material which are subjected to use. So, considering the temporary heat treatment process, temporary is an aspect of heat. So, we have other heat treatment processes, but our major heat treatment process here is temporary. Temporary is an aspect of heat treatment that involves heating a material to a subcritical temperature, soaking that material for a time duration in the furnace, then allowing that material to cool in still air. Allowing the material to cool in still air. So in the course of performing our experiment, we considered samples of different medium carbon scale samples which are obtained from the open market. These samples were subjected to compositional analysis, which we also call spectral analysis, just to determine the chemical composition of the test samples and ascertain that the material that we are using is medium carbon scale. And the compositional constituent of the material is as shown in the slide. Then after which a metallographic examination is conducted, the essence of metallographic examination is to know the morphology, just to know the microstructural view, just to view the microstructurally the material. Now the heat treatment process involves subjecting the material to heat and allowing the material to cool. Then after which the material is hardened. After the hardening process, we now quench the material. That is quenching involves hardening the material. Then the major essence of tempering is to relieve internal stresses in the material. Once you have a very hard material, yes, hard materials are good. You understand?
Hello, sir. It just goes straight to the point. What you do, how you do it, and the results.
Okay.
Yes, sir. Thank you.
Okay, let me go to the results. Alright. From the results, we can see. Go continue. Of the material. The dark region is the ferrite region, where the white region is the ferrite region. Then we can also see the effects of temperature on the different mechanical properties. So tempering reduces the hardness of the material, also reduces the tensile strength of the material and the toughness of the material, while improving the ductility of the material. So in conclusion, we can conclude that tempering influences the mechanical properties of the material. Thank you.
Of course, we all do know that steel has mechanical properties like Young's modulus, Poisson ratio, and others. He tried to use tempering heat treatment to improve the mechanical property because of the need to have balance of strength and toughness. Thank you very much for the presentation.
So that brings us. He is the last presenter for this session, and we believe that you have your questions there, ready for all of the presenters. We are going to take it this way. If you have a question, you raise your hand. We invite you here to the podium. And you mention the name of the presenter who you are directing your question to. Do we get that, please? Okay, so can we?
My name is Engineer Samuel. My question goes to Dr. Bill on your second paper presentation. From your study, I didn't see any treatment replication. So how come you do your conclusion based on simple observation from treatment? What is the level of significance of the test conducted?
Is that all the questions you have for me?
The second question. Yes, that there was no replication. Just did one measurement, yeah, for the test.
Before we take the question, we want everyone.
My name is Dr. Seet. My question is, the depth of penetration decreases as the frequency increases from your results. Please, can you tell us the implication of this and what frequency do you think is safe?
Asking about validation. Now, replication of the experiment. First, if we want to complete all that, we don't have space. But you can see that the test was made for 4 frequencies. The test was made for 4 frequencies. And that, I believe, answered the question of validation. The second question, he said, when frequency is increasing, the depth of penetration is increasing. It's not so. It is when frequency is increasing, the depth of penetration increases. Now, what is causing this is because conductivity is increasing. Now, electromagnetic wave, when it enters a medium of high conductivity, it is hindered from penetration. Instead, it is absorbed quickly at the surface. So, for the 700 can penetrate deeper, but it doesn't have enough energy to cause any harm at that point. But when the frequency increases, the penetration is remain at the surface of the scene, more and more to the surface of the scene. So it doesn't go deep when the frequency is higher. This is because the conductivity is increasing. Because the propagation of a wave is determined by the dielectric properties of that medium. Does that answer the question?
I hope that answers the question. Can we give a round of applause, please?
I think we are wrapping up this session, please. Sorry. A contribution. Okay, please come and do that quickly.
I'm not sure time. Let me just go straight. I have other questions, but this is a contribution from the first speaker. The speaker said that the compressive strength of steel is less. That steel is strong, but has less compressive strength, whereas concrete has high compressive strength and low strength in tension. This is not correct. This is not, this literature, it is not correct. Steel has a compressive strength in the range of 20,000 to 125,000 psi, whereas that of concrete, the compressive strength is just between 4,000 to 20,000 psi. So steel is much stronger in tension and in compression more than concrete. But in reinforcement, we use steel just to improve the tensile strength of the concrete. And at the same time, why we use bamboo in the first instance, it is not a match for steel, but the bamboo is cheap, is what is just bringing to the land life, and we can understand where it's coming from. Thank you.
Those for technical session 3 and 4, please, we shall all be moving down to AC12. AC12 is just open here. The moderators there, Dr. L, Dr. L, Dr. Mrs. I.C. AKK, and Dr. L.C. Nato are the moderators for technical session 3. Technical session 4, Dr. O.C. Mungo, Engineer Dr. O.C. Mungo, Engineer Dr. C. Onoha, and Dr. Mrs. A. Izuku are the moderators for session 4. Let's all move back to AC1.
I am Akachu Kumobi and I'm presenting on behalf of the group. The design and optimization of sustainable hydraulic structure for gully erosion control at Naked. Of course, we know that erosion is a global problem that involves the removal of soil particles either by man-made or
natural factors such as air, water, and wind, water, and erosion globally. And the erosion costs almost $8 billion per year. Erosion costs almost $8 billion per year, and Nigeria loses 350,000 soil hectares per year by erosion, and this by Newman. And southeastern Nigeria has some of the fastest expanding gullies in Africa. So to deal with this problem of erosion, our case study is Umwala Nekede. So with our GPS, we're able to capture the location, and we analyze the geology of the area, the hydrology of the area, the kind of rainfall we have in that area, and we see the impact of erosion in this area, which is farmlands are destroyed and roads are cut off. So it begs the question, how do we mitigate this problem? And the simplest way of doing this, or the most sustainable way, is to make way for the water. By building a very sustainable hydraulic structure to allow the water pass. And for us to do this, we made use of some of these tools such as the global mapper, the GPS, handheld GPS, and the shorter radial topographic mission, combining this with GIS to get every information we need about the watershed in order to design a good hydraulic structure for that region. And Firstly, we carried out a watershed analysis concentration, which is the time it takes water to move from the farthest part of that aquifer to the outlet of that catchment area. And the time of concentration is a function of the overland flow and the channel flow. And for us to really get these two parameters, we make use of the Kebi formula, which is a classical formula, and the Kebi method. So for us to get the overland flow, we make use of this model, which has been accurate, and it's been accurate owing to the parameters we gathered in that given catchment. We carried out hydrologic analysis using the time of concentration to get the intensity of the rainfall in that area. After getting the intensity of the rainfall in the area, we went ahead with this to get the slope of the area, which is just a function of the upstream elevation and downstream elevation of the catchment all over the maximum length of flow. Now, after getting this, we use it to get the peak rain, the peak flood that we can get from this area. With this peak flood, we can now design a sustainable channel that can carry out this flood, hence mitigating the problem of erosion in that area. And to do this, we proposed the use of a horizontal channel and getting the area using these classic formulas, and after which we were able to calculate the wetted perimeter, and then we went ahead to calculate the velocity of flow using the classical Manning's formula, and then we went ahead to calculate the discharge from there. So if the discharge we get at the end of the day is greater than the peak discharge we calculate using the hydrologic parameters we gathered from that watershed, it means that our design is not sustainable. So with this, we're able to design a very good channel to convey the amount of water coming out from that region. But as a matter of safety, we also added parameters such as freefall and the top width to make sure that in case there is any overflow in the catchment as a result of maybe rain exceeding the return period, any flood exceeding the return period, we're not going to have a disaster in the region. So finally, by the time we carried out some of the analysis in the region, we got some of these which I'm not going to list out. So but it was what informed the decision we took in the design. And at the end of the day, we thought we carried out many other analyses to get using the classical formulas I showed you to get these various figures used for the design of the channel. And lastly, to just round it up, we discovered that designing a good hydraulic structure to convey runoff from that catchment has to do with involving both the hydrologic parameters and the basin parameters. So the peak flow from the watershed should be highly considered in every good design, and a sustainable hydraulic structure must be durable, affordable, and eco-friendly. Thank you.
Need for a coupled approach for real-world performance evaluation. Like I said before, that's exactly what it is. You know, working, you know, like we say, 2 years are better than 1. So So combining the two together, that is what it's giving you. Applications: photovoltaic, thermoelectric, hybrid photovoltaic thermal energy system, nanoscale absorbers. What's happening?
Okay, so you did some simulations, and these are the results.
This is the result of the simulation. This is showing how the heat is distributed in that material that you are using. You see your solar panel. You look at it, it's like a glass surface, isn't it? The actual material that is absorbing the photon is there. So the material, we're talking about the temperature with time, and this is the position, the thickness of the material, 10 centimeter. Here we have 0.001 meter, which is 10 centimeter. Now the time, this is also picked at random. It's not a complete calculation. So T is equal to 50 dt. By the time you put the value, whatever value into this design, you get what you're looking for. So this demonstrates the distribution of the heat in the temperature in the material. You can see that at a lower temperature, as the frequency is increasing, the temperature is increasing with distance. At higher temperature, you can see the slope is dropping not very fast. But at lower temperature, you see it's almost at the bottom. Here, the sun's ray is touching and creating the heat and the sink. Because if that is not happening, there won't be the power generated. So, just like you have the potential difference, you must have the high heat section and the low heat section. And this, we use Newman's and Joshua-Wick's boundary condition to achieve this. So we have the boundary condition at 100 degrees Celsius and 25 degrees Celsius. So, conclusion. It follows EM penetration pattern. I think that's part of what I just discussed. The key takeaway: coupled EM thermal captures core physics of solar harvesting. Then the MATLAB simulation, which we visualize the temperature dynamics effectively, boundary condition and material parameters, shape energy efficiency. So for future work, model anisotropic and layer the media. Then explore non-structured observers, 3D geometries. And finally, integrate real solar spectrum and dynamic illumination. So that, in a nutshell, is how you theoretically explain the combination of the photon energy generation and the solar heat energy generation and combine them.
A round of applause. J.S. Nzube with K.C. Chinedu, C. Chiabotu, and R. Uche. The representative will be presenting on the topic titled Design and Development of an Automated Car Wash using a PLC brand system. Okay. Design and development of an automated car wash using a PLC brand system.
Titled The Design and Development of an Automated Car Wash using a PLC-based system. This is in line with the introduction of the smart city, urban engineering. With increased demand in efficient and hygienic way of vehicle washing and maintenance, the introduction of this system is going to solve the problem we have when it comes to manual washing of our vehicle. Introducing this system will help to save labor, cost efficient, and we are in line with the introduction of the smart city and urban development. When it comes to the problem we face with our normal traditional way of washing car, which is the manual way, it's the consumption of excess water relies on heavy manual labor, lack in consistency of
cleaning, and integrating with the smart infrastructure framework. Like we all know, this is an automated system, and we know in our current industry the vital role that automation has, starting from the production industry, our refining industry, and the rest. So,
I think you should state the objectives. They're very important.
Yeah. The main objective of the study was to design and develop an automated car wash system controlled by a PLC. A PLC is a controlling system, or it stands for the programmable logic controller, the control system used in the industry that helps to automate different kinds of systems. It helps to save labor and makes things faster. And to automate the entire car washing process, including the soaking, the scrubbing, the rinsing, and the drying system. Programming this programmable logic controller in order to suit the need of that particular system, ensuring safety and reliability by integrating safety sensors, feedback loops to monitor operations, provide multiple consumable washing, and integrate the use of IoT in the sense that the owners of this car wash can know the number of washings done, how much they have been made, can monitor the system and change it based on the need of the users. This system reduces manual labor, ensures consistency in cleaning, and minimizes the usage of water. The materials in this system, with the use of special instruments like the valves, relays, blowers, pumps, brushes, and our main mastermind, which is the programmable logic controller, this system can be achieved. Why we focus more on the PLC is that in our modern industry, this PLC has offered a lot to us. And in terms of making work easy and giving us smooth processes, this has made it possible. So these are the processes involved on how the car wash will be made. When the user of the car wash brings his car, he parks it in a good position. Then the system starts. When you make your payment and do everything involved, select the type of washing you want, you can start with the soaking, then the scrubbing. After the scrubbing, the rinsing, then the drying of the system. These are all done automatically. So in this system, there are different design processes that are going to be involved, starting from the mechanical and the structural, which is the bay. The civil engineers will design the bay where the car wash system will be developed. The mechanical engineers will do the metal work and everything. Then when it comes to the wiring and components of it, the electrical engineers will come with the installation of the sensors, the motors, the pumps, and lots more. Also the electrical engineer will do the programming of the PLC, because this PLC can be programmed to anything we want, anyhow we want to make it work. Then the commissioning. So this is a sample of video.
At least you've seen what it looks like.
Continue. Okay, this is the video. This is going to show the video of the simulation of how it's going to start from the pre-soaking, which is going to soak it with a detergent, down to the scrubbing, down to the rinsing, and down to the washing. These are all sensors that indicate that yes, this vehicle is ready to enter the next process. And this process will have a water recycling and have lots of features added to it. So this is the design I made, and by God's grace, this project was designed, a prototype, a working prototype of this project was designed early this year. I was used in my final year project on February, supervised under Professor Benuche and Engineer Chukwuebuka Kinsel. So as you can see here, this is the water recycling component. The working prototype is at the department. This is the water recycling component with everything here.
The time is almost up.
So this is the process or the program. This is how it will look like when you're inputting or writing the program in the PLC. So, with this process, the average working time of this, the average time you can use to wash a car is about 3 to 5 minutes, which will save you time, unlike the conventional manual process, which takes over an hour, and the consistency in the manual process isn't very high. The primary aim to to develop an automatic car wash using PLC technologies to improve the efficiency, reduce manual labor, and ensure a high quality washing. Consistent washing process. The proposed system will be reliable, cost-effective, easy to operate with an automated control and safety feature. It offers a valuable upgrade to the traditional and car washing system.
Wow, that would be a very wonderful.
After I reviewed a paper for International Journal of Environment and Climate Change in Iowa about heat stress and heat index, I felt that we in the economic topic we should be to have the knowledge of these things. Because when I reviewed that, I discovered that most of them were having stroke there. So to do this work, heat index, what is heat index? Heat index just means the air temperature, what the relative humidity could do to the air temperature to move it up, to bring it up. And what is relative humidity? Every level of temperature has a capacity to take moisture. But the moisture in the air may not be to that capacity of the temperature. If the moisture in the air is not to that capacity of the temperature, then the temperature can absorb more moisture. But in a case where the moisture in the air is so much that the temperature can no longer absorb moisture, that is the critical stage. Often at time you may be at night, you see yourself sweating profusely. Ask yourself why. The windows are okay, ventilation okay, but you see yourself burning like you had a bath. It's because of that. The moisture in the air is so much that the air temperature is no longer taking what comes out of you. Are we communicating? So this thing comes like that. To get the data for the study, I went to 9 months.
Can you present the data with slides?
The introduction. The air maximum temperature and the relative humidity of this place, State. Now, before transferring to heat index, I transferred with statistical package for social sciences to see how they correlated. I discovered that any change in the relative humidity will cause over 80% change in air maximum temperature. That gave me the correlation. Now, to the heat index proper, these are the data of the heat index. But going back, this is the air maximum temperature. The heat index chart, when you take every value of the air temperature and every value, like this January, you take the value of January and you take the relative humidity of this place, you go to the heat index to give you the heat. If you go to the heat index chart, you see the heat index of this point. So I got the heat index of the whole month from 2008 to 2026 of each of the months. One thing I discovered that the relative humidity was able to cause an increase in the air maximum temperature of not less than 50%. Look at that. And through nature, I discovered that when the air temperature is just about 35 degrees centigrade, heat-related illnesses could occur in human beings, like heat rash, measles, stroke, cramps, you understand, exhaustion. So then, if the temperature, if the relative humidity is able to expect our air maximum temperature to like 60 degrees centigrade, from 2008 to 2023. If you check, it's just that they say we should give 5 pages. If you check through the study, I discovered that I got from 37 degree centigrade to 60% degree centigrade because of the fine-tuning of our relative humidity, which means that we are exposed to these related sicknesses. So it's not a function of going to the hospital. It's important to know what causes what. So this temperature is exacerbated by relative humidity in this place. So how do we go about checking this to live long? Now, my advice is this. If you have fan in the house, maybe the place is hot, and you on your fan, be careful. Allow the fan to be blowing. It may blow hot and give you hot air. Whereas the certain this thing is not in the room. It's in the atmosphere. It's in the atmosphere. One other thing I will advise us, anything you do like generator sets, activities you do that will exacerbate moisture, evaporation of moisture, let us reduce it. Because the more this moisture are evaporated, the one will expire, expiration. When you expire, the water vapor may not get out of you to refresh you. It becomes a problem. So you're welcome. That's it.
I think most of the presentations here are about things we witness on our day-to-day activities. Like sometimes we get warnings either from the internet or from the media that so the heat waves are going to be high, and you are advised to moisture yourself with water. And this is a typical example of another method that you can apply to be able to help yourself out during such conditions. So thank you, Mr. Oja, for this presentation.
In other words, if we can take care of our environment, we are indirectly taking care of our health. Thank you very much, sir.
Thank you. Engineer Professor Remy Uche, fellow Nigerian Institute of Engineers, and the Dean of the School of Engineering, Federal University of Technology, Owerri.
How
Thank you very much. You know that conferences are an integral part of academic teaching and research. At conferences, we try to do an expose of your research products. At conferences, you meet colleagues from different locations with different mindsets to exchange ideas and views on the current trend. So when I came into as the Dean of Engineering, I discovered Futo that was established since 1980. We have never had an international conference. For me, it doesn't sound good to me. And I think if it is, we have to bet the jinx. Like other people live here to go to United Kingdom to deliver lectures. People can live here to go to the US or other areas to hold international conferences. And our university that are built on quality, people cannot come to us. I say this is not a bad, it's a bad trend. So look, we must break it. And that is why we consider this idea. You have to hold a conference that you can attract scholars from all over the world into our own vicinity.
one would wonder how we were able to gather what has happened very much aware. How were you able to do that?
Good. So when there's a way When there's a will, there must be a way. There's a way to do this. And by the grace of God, we mobilize personal resources to ensure that we put on record this landmark history of our university. And it's delivering this conference that has attracted scholars within Nigeria and also outside of it. Yes.
Because that is great. One of the speakers all the way from Newcastle to Harvard. What are the major takeaways?
Sure. One, it has given room for networking. It has exposed people to the energy transition. They're moving away from the fossil fuel to other ways of energy use in the country. So people can see papers were delivered within this team area. It's something so wonderful. People are going home so enriched about other sources of energy and how it can be deployed to live off the fossil fuel that even affects the climate. So we're going green. So this conference has taught people that we can now go green. Then we can now have energy that's less harmful, that's eco-friendly in our society. That's it.
I know you're a man of gratitude. You have people you want to appreciate.
Good. The members of the committee, first of all, the chairman of the committee and his team, and even yourself, Ojuku, and Master Dean. These are people who supported the vision. And also some of the head of departments, some individuals who also contributed personal resource to ensure that this milestone is achieved. The Vice Chancellor of our university, of course, she gave us the bus that meet people, over the conference center, even the AC fuels here. We use them well. And also Professor E. Anyanwu, who came in less than 5 or 6 days to speak at one of the keynote speakers. And Enyoko that came from Newcastle University. It's not only that came from there, but it's a young man with global visibility. Came there on personal resource and convenience. Yeah, I think it's fantastic. I'm so grateful to him. Every member of staff who have contributed in one way or the other. My gratitude goes to them. And forever, I will be grateful to them. Because we have broken these jinx. That's this resilience, this reluctance of not be like others. Other ones will build on the successes of this. Because progress is making two where one exists. Now we have done this. It's not the end of it. We are going higher and higher. The next edition will be better than this. And I'm looking at having this conference once a year. Annually, 6 months. Because of where we are. Our university is a brand name. And of course, and what we have done, this is live. Like people are listening to it live. I'm sure the next edition will be super. That's right.
Very much.
Yes.
We carried out in Scandinavia, and then one, yet it gave about 70%. We still have carbon dioxide contained in the biogas. So that's not a viable option. It contains 40 to 75% of methane, 30 to 55% of carbon dioxide, and traces of hydrogen sulfide, and then we look at the calorific value of 23.1 to 25.7 megajoules of yes. So what look at methane, 35.8 to 39 kilojoule per meter cube. Biogas needs to be upgraded. Therefore, we need to upgrade that biogas again. So talking about anaerobic digestion, we have gone past that stage. Engineers are thinking, critical thinking. What do we do? So now, upgrading method, pressure swing. We have pressure swing system. You do what? You purify the biogas. But where do you send the carbon dioxide? Still environment. You practically do nothing. You're leaving, pushing the carbon dioxide into the environment. So we don't use that. Now, there's a system called power to gas. Power to gas. How
hydrogen, then store it, then distribute it. Because the renewable energy we're talking about, the solar, this and all this one, they are inflexible. Due to the inflexibility of the renewable energy sources, if they start here, both when you demand it, you need it, it will be there. When you don't need it, it will be there, wasting away. How do we save this energy? So we use green hydrogen. We use the system called power to gas. That power to gas now, we produce hydrogen. The prof was asking, how can we produce hydrogen in Nigeria here? It's very simple. Green hydrogen can be produced. Sea water, use it, then use electrolyzer and do what? We produce hydrogen. The green hydrogen, that clean one is talking about, not the petroleum one. So this green hydrogen now, once you produce it, now you now use it to do what we call, to now power a biomethanation plant. The process is called biomethanation. You volatilize the carbon dioxide using that green hydrogen to do what? To produce methane. And studies have shown that yes, we can do that. So here, biomethanation becomes a viable option to convert this carbon dioxide and hydrogen produced to form methane for storage and distribution. We will show it here. Methane used for space heating, gas fuel, electricity through CHP. So now this is the system, this is the model, this is the system, how it works. These are renewable energy rays, wind, solar, and all that, electricity, grid, whatever, get to electrolyzer. Then from here, storage. The storage is working with the biomethanation plant. Here is biogas. That's anaerobic digestion. We're no longer talking about anaerobic digestion. We have gone past that stage because it can't give us the 95%. Because remember, the natural gas that is being used now is about 95 to 100% of what? Methane. So you must convert the waste, the biogas, to 95% of methane to be able to use it in CHP. Else you are just destroying the whole distance. To be able to use it for years, CHP and other things. Okay? So the biogas now that is produced here, which is about 60% of methane, you now inject it into this one is biomethanation process. This is where we come in. Okay, so now this biomethanation process now, we have two methods, in situ and ex situ. The in situ is the anaerobic digestion, producing the biogas, then you push it into the biomethanation system. We have the TBR, the triple bed system, we have the bubble column reactor, we have the CSTR. But this CSTR and the TBR and this CSTR and TBR, CSTR, okay, CSTR contains a moving part. Because we don't want to design something that will also be consuming energy. So, bubble column reactor and TBR, these ones don't have moving parts. Okay? So from here now, you convert this methane to what? 98%. Yes, of methane. So now, problem area, gas liquid mass transfer, that's the major problem. But I'll explain this. High hydrogen partial pressure, VFR accumulation, carbon dioxide inhalation, rising pH, microbial adaptation. So now, these are the research objectives, what we need to get. So let me explain this. See the system, see the methodology. This is how it works. The biomethanation system. So what you do is, you get this digestate from the anaerobic digestion that has already finished. You know, at that point, what we have is methanogenesis. That point is methanogenesis, where we use hydrogenotropic methanogens. That is what works here, and convert hydrogen and carbon dioxide to what? Methane. So now, what we did, get these vessels, but here what we use is ex situ system. That was why I was asking them. Ex situ system is where we are going back to what? Carbon capture. Okay, just 1 minute. The carbon capture, this is where we get the carbon capture. This carbon dioxide is captured from the environment, from all activities. Captured, used with the green hydrogen, injected into this particular bubble column reactor through a sparger. And this is where we have hydrodynamics engineering. This hydrodynamics here now helps us, you produce 98% of methane is produced here. That's what is produced here. Look at it here.
Total resource.
So that's the methodology. Then,
okay, tell us the conclusion.
Okay, that's the look at it. So look at anything here. Look at it, running. Now this is for 42 days. From 31, from here, sorry, from 28, from 22 days to 32 days, we have what we call steady state. Steady state where it's producing the highest level of methane. That is at this point. If you exceed there to sparge more gas, it comes down. So this is what we used to do this simulation, ANSI fluent with UDF. That's what, because you have to run a modeling itself. And then from there, this is what we got. That what this means is that you can actually stay in your house. Impute hydrogen. This is the quantity of hydrogen we are going to impute. This is what you are going to get. This is carbon dioxide we will impute. This is what we are going to get. But the stoichiometric reaction is 4:1. The 4 is that is stoichiometry. I think the reaction is there, but maybe later we will get this thing. So this is the conclusion. High methane production rate 3.2. BCA was successfully used to upgrade the methane to 95%. There was high hydrogenotropic metallurgic adaptation. The simulation shows that the output parameters can be predicted. The simulation shows that the process can be optimized further, and it is possible to scale up the industrial process. Then recommendation, we can use, okay, these are our recommendations, government investing on that and all that and all that. Yes.
At this moment, so that we round up. If we have questions,
please raise up your hand.
The first question is going to the first speaker. Please, I would like the first speaker to tell us the safe concentration of these heavy metals. Because in the experiment, I came in a little bit late. So I want to know if he stated the safe concentration. Yes, the person that is talking about Umedo. That's the second. So he mentioned report fantastic, arsenic clear and all that. So please, by the UN convention, what is the safe limit of this heavy metal? And in the experiment, I want to know what is the concentration of this heavy metal in the first ripe fruit, so that we can compare for ourselves and know that yes, this experimental is actually higher than the safe limit.
All you have asked, I've already presented it. I gave the same threshold from WHO and FAO for each of the heavy metals, and also showcased how calcium carbide and paracetamol exceeded the safe level. Yes, it was there present.
Thank you. My name is Dr. Hugh Odrizo. My question goes to Mr. Pascal. Okay, during your presentation, you mentioned that you were able to enrich your snack with raw materials that are active in antioxidants and bioactive components. So I must commend that your work. But my question now is this. What informed the composition of that your snack? Because you mentioned that you made use of turmeric and ginger.
70, right? The cassava.
So what informed that composition? And secondly, on taking that snack, can someone be able to get the daily permissible composition of these antioxidants?
Inclusion of the spices, ginger and turmeric, is on account of the fact that though cassava is rich in carbohydrates, Groundnut is also appreciably rich in protein. But both lack these vitamins and also antioxidants, which we can source from the ginger and the turmeric.
Wow.
Yes, they are rich in antioxidants. Yes, in terms of dietary requirements, daily dietary requirements, they are not enough for daily dietary requirements. So what it means is that it's not just the snacks you take alone in the day. You still have other things to eat that can add to your recommended daily allowance. Thank you.
Yes. Is there any effect for excessive inclusion of the antioxidants?